Welcome to the UEFI Forum webinar. We will begin here shortly. Hello, and welcome to the UEFI Forum webinar, Secure by Design and Zero Trust Architectures for Firmware, presented by Phoenix. Our presenter today is Dick Wilkins, Principal Technology Liaison at Phoenix and UEFI Forum board member. I'll pass it off to you here, Dick, to get us started.
Well, thank you very much for that introduction. You can see all the gory details there. I've been far too long in this industry and teaching computer science and that kind of thing for many years, and I hope to pass along some of that experience to everyone here. So, very quickly, the agenda for today is I'll do a very brief introduction. We'll talk about Secure by Design, what is it, etc. Then Zero Trust Architectures, summarize, do a brief call to action, and have a Q&A session. Just feel free to enter your questions to the system along the way, and the folks will gather that information up and we can get started, jump right into questions. So, introducing things generally, Secure by Design is a U.S. government initiative in the cybersecurity space that's being actively picked up all around the world. There are ISO/IEC 2700 series standards on it. The European ETSI has a technical specification 103, 645, etc. that have picked up on this Secure by Design approach. And one of the tenets of that, which we'll talk about specifically, is this zero trust architecture. So those are the things we'll be talking about in today's session. So the government, United States government, is requiring that products, particularly those used in critical infrastructure, must be developed using these principles. Since computer systems, general purpose computer systems, be it laptops,
I'm not quite
desktops.
sure how to help you with that.
Sorry, Alexa's giving me a hard time here. Anyway, that since general purpose computer systems and laptops, desktop servers, etc., are all pulled into critical infrastructure, it basically means that everybody that's developing firmware for platforms, all UEFI platforms, really need to be thinking about this. EU, that the GDPR portion of the EU programs are requiring them, and additional jurisdictions around the world. And really, when it comes down to it, it's really just kind of the right thing to do. We should all be thinking about these principles. So, what is it? Secure by Design means technology products are built in a way that reasonably protects against malicious cyber actors successfully gaining access to the device, their data, and the connected infrastructure. This is pulled right from the government document. It's what CISA and the other 3- and 4-letter agencies of the U.S. government believes this means. So it means that we have to care. And they describe it also as this is a holistic design approach to developing software and firmware. It's not something you can bolt on afterwards or test in. after the product's been developed, you must make it part of the design process. You need to be making investments in technologies that provide additional security, even if you can't really sell it. Having been in the industry a long time, I've seen so many cases where the marketing guys say, we don't want you to work on that. We can't sell that. We want you to work on something that we can sell as a add-on or a special feature or a differentiator of our product, whatever. That security stuff, that's just noise. But that just doesn't work in this environment. You need to be prioritizing features, mechanisms, implementation, the tools, etc. Don't be adding on things that are appealing or marketing fodder, but really just enlarge the attack surface and don't really add much value. It's just in the product management space, we call it gold plating, adding features to a product that really don't make any difference, but in some ways just make it worse. One of the tenets also is this idea of secure by default. Security configuration should be the default. It should come, the product should come secure. It's configuring it for security should not be a customer's problem. They shouldn't need to figure out what ports they need to close, what options they need to select, whatever. It should come secure. And then if you need to open things up in order to allow a customer to do a particular operation or whatever, they should do that with knowledge and planning. And most importantly, you shouldn't be charging extra for the secure version of your project. You shouldn't have a normal product and then have a SKU that, oh, that's our secure version. We charge a few $1,000s extra for that. That's just a no-no. So generally, the US government's position is, their principles behind this is any company, developer, product team, whatever you want to call it, they're responsible to take ownership of the customer security outcome. How does it work for the customer? Is it safe and secure? Does it end up being safe and secure after they've been using it for a while? It's the developer of the product's responsibility to make sure that they enable a secure customer experience. You need to embrace radical transparency and accountability. You don't need to be hiding stuff and pretending that it's not happening. And when things go wrong, you have to own up to it and say, we messed up, but we're fixing it. Or we have fixed it, and here's the fix, whatever. And then you need to build an organizational structure and leadership to achieve those goals. That's an important piece of this. So we'll talk about each one of those a little bit more. Take ownership. Best practices dictate that firmware developers invest in security efforts that include code hardening, strong security features, appropriate defaults, etc. You need to ensure that all user input is validated and sanitized. Running my words together here this morning. Use memory-safe programming languages where possible. Obviously, there's an awful lot of C and C++ floating around, but where we can convert to Rust and other similar languages, that's a great thing. Use a software development lifecycle process. Having taught college product software development for many years, I've observed the just point me at the problem and I'll write some code to make it work. And then we'll figure out how to fit it into the environment. That's just not acceptable. Agile development is fine. You don't have to do waterfall to have a software development life cycle, but you really do need to have a documented process that you follow. Then last, we all should be converting to post-quantum cryptographic functions wherever that's possible, and we should be making it possible everywhere that we possibly can. So, secure by default practices. Any security critical code, and really pretty much everything, ends up being security critical in firmware, in platform firmware. But obviously, remove default passwords and test keys, that kind of thing. We see so often that this keeps happening over and over again, where we deliver code maybe to a partner who's going to convert it into a final product, and we tell them, remember, take those default passwords or those test keys that we have in there, take those out before you ship it. But what happens? They always end up shipping it with those keys in there. Consider using penetration testing. Discourage unsafe old legacy features. Try and get people to stop doing that. Make sure that you're using open source responsibly. Open source is critically important in our infrastructure and our world of software firmware development, and much of it can be very high quality and well vetted, etc. But make sure that there are appropriate maintainers and there's the appropriate process being taken care of in that space, that they're using appropriate software development life cycles to create the open source product. Implement vulnerability management in your environment. Foster firmware development workforce that understands security. Try and hire folks that have security sensitivity and security training, and then offer it to your workforce, and make sure that the people are taking the time to understand how to create secure products. And then, as we're going to talk about later on in the talk, create a zero trust architecture design for your product. Okay, examples of security code, critical code for a firmware. What kinds of code require this kind of practices? Really, pretty much everything. But let's talk about some obvious critical stuff. Runtime services interface, stuff that's around when the OS is around. OSs are notorious, and having services being called by them, you got to assume that they've been attacked and they have vulnerabilities, and stuff's going to get passed to you via runtime services interfaces that's not valid. Management mode, SMM on Intel architecture platforms, Trust Zone and ARM, that kind of thing. They tend to be very protective. They and they manage those security critical variables and etc. And you need to make sure that they are well managed. Anything that loads boot images, code that executes at boot time, drivers that perform device discovery on external ports, drivers that receive and parse network packets. It didn't start out to be a problem, but as UEFI has grown over the years, everybody wants to be able to talk to the network. And so if you receive and deal with network packets, that's just another path for input. In short, as it says, any code that receives or uses untrusted data. anything that could be an attack vector, which is pretty much everything, needs to use these secure coding practices. Continuing on, embracing radical transparency. Publish aggregate security relevant statistics and trends. Show how things are going in the industry, to your clients and customers, how they're going with your company. Keep statistics, understand them, and make them public. Publish an attestation to your software development lifecycle. Document what it is, make sure your developers are following it, and tell your clients and customers that here's what we do and how we do it. Publish software bills of materials. SBOMs are a hot topic right now. We should be all publishing these things. And sometimes there's pushback from our customers or whatever, that they're concerned that exposing the content of their products may open them up to either attacks or liability of one sort or another. We've got to get past that, folks. This is, we've got to be open with what's in our products. Publish a vulnerability disclosure policy. Tell people what you're going to do. Have a policy, first of all, and then publish it so that everybody knows that. And then embrace vulnerability transparencies. Publish the CVEs. Make sure that you're putting it out there, that you're documenting the vulnerabilities that you discover and how you're dealing with those. Of course, embarrassment is a motivation to do better in that situation. And this is one that you're going to have to work up the chain of command. Probably most of the folks listening to this presentation today are not going to be able to directly deal with this, but talk to your management about it, push up the chain of command, try and get folks involved at a higher level in your organization, at the executive levels. We should have a secure by design program in all of our efforts, and it should be part of our regular corporate reports. We should be providing development, engineering should be providing reports to the board of directors on what you're doing and how it's working and what your next steps are, et cetera. Publicly name and empower a secure by design senior executive, VP level type person maybe. Say, this is the person that's responsible in our company to make sure that we are doing secure by design. Create meaningful internal employee incentives. Incent people to do the job right. Whatever that means in your organization, in your situation, but whether it's promotions, pay raises, bonuses, whatever, but incent people to do the right thing. And consider creating a secure by design corporate council, sort of an executive level group that will talk about secure by design and make sure your company is following it. So these are things you're not going to be able to do yourself, but you can make happen through pressure. So that's secure by design. Now we're going to switch over here and talk to one of the particular tenets, an important one for under that secure by design umbrella is zero trust for firmware. And zero trust architectures in general, the term was created in 1994 by a guy named Stephen Paul Marsh in his doctoral thesis on computer security. It was further developed in the early 2000s, and in 2018, NIST published their SP 800-207 on the zero trust architecture. So it's been out there for a while, folks. If you haven't taken this to heart, you should definitely be thinking about how to do that. So we're going to talk a little bit more about that. So what is this thing? Trust, fundamentally, the assurance that one entity holds in another that entity will perform a particular action according to a specific expectation. You trust somebody to do something when you believe they will do what you expect them to do and not anything else, will not leak your data or whatever. They will, and they won't ignore you. That you trust them if they will do these things. So what's zero trust then? Well, it's a catchy phrase. It's great for a paper or a press thing or whatever it is, but it really is something of a misnomer. You have to have trust at some point. You have to trust that somebody you're communicating with in a system of firmware and software, that they will do what you expect them to do. But as I say here, applying the principles to systems and firmware is really understanding the difference between implicit trust and explicit trust. And we're going to describe that here. So implicit trust is essentially just trusting people because they meet your expectations. They're on the right network, they're in the right location, they've called an interface that you expected them to call. You've assumed that somebody else has validated that they are who they say they are and will respond appropriately. Whatever, it's the assume thing. I'm sure everyone's heard the assume is broken down to makes an ass out of you and me. It's zero trust or implicit trust, or the Zero Trust Initiative declares that implicit trust is a very bad idea. Never blindly trust, always verify. And I like the old Russian proverb that Ronald Reagan put out there, trust but verify. But in this case, we really should be doing verify and then trust. So, I've kind of alluded to it, but this is the kind of situation where you assume that because you're a service you're talking to on a network connection is on a private network, a private backend network that's walled off from the rest of the infrastructure, you're okay. You can just assume that service is okay. We know that that's not actually true. We've seen at events like Black Hat things where folks have demonstrated that an operating system that's vulnerable can attack a BMC, and vulnerability in a BMC can allow access to a back-end network, and that BMC can pretend to be any kind of service it wants to be. And that's just an example of the kinds of things you can get yourself into trouble with. We had an OEM a few years ago in the UEFI space deliver the latest firmware diagnostic capability and shipped a bunch of products that allowed them to connect the firmware to connect to a service in the cloud to run diagnostics, et cetera, and expose control points. And it turned out that person in the middle attacks were quite really with that. They just assumed that because the service they connected to in the cloud had the right name and talked via the right protocol, that it was the service that they thought they were talking to. And in fact, wasn't necessarily. And very quickly that interface was attacked. So, and they had to recall all those products and pull that interface completely out. So we said implicit trust is bad. What's explicit trust? It's where a trust relationship is known and defined and can be assessed. There's a root of trust, a chain of trust from that root to the trustor and then on to the trustee. And the final trustee can verify via one type of attestation or another that the entity they're talking to can be trusted in the context of their expectations for that trustor, basically the person providing a service. And this applies, obviously, we talk about this and networking jumps to mind, but it really doesn't have to be. It can be an OS talking to firmware. It can be one part of firmware talking to another. Firmware on a boot device talking to platform firmware. It's endless. Any place that somebody's calling you or you're calling out to somebody else, or somebody's generating a system management interrupt, you need to be able to verify that they are who they say they are and they're not going to abuse your trust. So isn't this just paranoia? The whole novel Catch-22 and movie said, just because you're paranoid doesn't mean they aren't after you. In this, we know that bad actors are looking for any way to attack system firmware. They're beating on it. So it's not paranoia to assume you must check everything before trusting it. An example of this would be, we saw a presentation by a low budget researcher that researcher had thought he had detected a potential flaw in the CPU to firmware interface. And so he went out and bought 15 systems off of eBay, used computers that used that particular chipset, set up a lab, and spent 3-4 months beating on those systems. Millions and millions and millions of attacks over months. And he characterized this unpublished CPU feature that was used by firmware, characterized how it behaved, and then was able to use that undocumented feature to access memory that he shouldn't have been able to access from user mode application programs running on an OS, and was able to change his privilege level by running a very simple program. Once he had figured it all out, he was able to run a very simple, very fast program to raise his privilege level and became admin or root or whatever you want to call it based on the OS. So these things are possible. Then if you think about this very poor security researcher without much funding, think about a nation state actor with potentially billions of dollars to spend, or organized crime groups or terrorist groups that are well funded. If this guy could set up a lab with 15 machines and run them for 24 hours a day for 3 months and find a flaw, you think that there aren't nation state actors out there buying expensive equipment, putting it in a lab, and then beating on it continuously, trying to find a vulnerability? They're definitely doing that. So we need to make sure that we understand that. So what do you need to check? Everything. API interfaces, code updates, any code or data retrieved from outside the firmware image itself, from the UEFI disk partition, from a network, no matter where you think it came from. Data can be used to trigger vulnerabilities, not just code. So it doesn't have to be bad code. It can be data. Talking about API inputs, you need to check to make sure they're valid values, there are no buffer overflows, no misuse of the stack, et cetera, all the standard stuff. The bad guys are doing what amounts to fuzz checking every entry point, looking for any kind of unexpected behavior. And this doesn't have to be a way to elevate privilege or something. It can be just denial of service. If they find that if they call your API with this funny input and it shuts down the machine, and just every time it boots back up, they do it again and shut it down, you've got a denial of service. Or if it bricks the machine, even better, then they cause people to have to reinstall firmware or throw the machine away, whatever. So also watch out for time of check versus time of use vulnerabilities. This is the kind of thing where the user can call your API with a valid value. You verify it sounds okay, but they still have access to the buffer, for example, and they can change it after you've checked it. And then when you get around to using it, I mean, this could be 6 instructions later, they have changed it. So you need to, anything like this needs to be moved out of the buffer to a safe location and checked independently, and then used from the safe location, never from the original buffer. Any code that gets loaded into your system must use, in a UEFI system, must use the load image code path. And paranoia is good in this situation. We have seen more than one case where someone says, oh, gee, the way you get, UEFI has documented that the way to get code into a system is to use load image. But load image automatically checks signatures and potentially logs things and extends them into PCRs and that kind of thing. I don't want to do that. It's a pain to get something signed. I'd rather just bypass that whole check and, oh, gee, I don't want to, that makes the system too fragile, too brittle. If I change the TPM values, then I can't unload my BitLocker key. So I don't want to use load image. So I'll just create, it's all open source. I can look at what it does. I'll just create my own code that does the same thing, but it doesn't do all those annoying things like updating TPMs and checking signatures and all that. We've more than once, folks have just said, hey, I don't want to do those things. I'm going to bypass. I'm going to ship a product without that. And guess what? Immediately, it becomes a vulnerability that at least exposes them to an embarrassment, but may well cause very serious customer problems. Handling secrets generally. Don't store passwords in raw text. Clear buffers. Remember, deallocation doesn't clear the memory contents, so there could be passwords and encryption keys and that kind of thing can be floating around in memory for quite a while. Always use approved, well-vetted encryption and hashing algorithms. Never roll your own. I've seen repeatedly folks have, they graduated from college, they're a new developer that joins your group. They say, hey, I came up with this really clever hashing algorithm or this really clever encryption scheme that I used in college. And I got an A on my paper and all that. So I'm going to use it instead of the standard library. Oops. And we find out that they're typically never as good as the well-vetted, approved security encryption algorithms. So don't do it. Code updates. UEFI firmware updates require signatures. Obviously, you're explicitly trusting the certificate authority and signer to protect the keys and do it right. This is a case where we're talking about, we say zero trust, but in fact, we're trusting the certificate authority. But you can't use unsigned unverified code updates. You can't allow rollbacks, whether they're signed or not, because if somebody does an update because they found a vulnerability and you allow them to roll back to a previously correctly signed version, you're allowing them to reinstall that vulnerability on the system. So don't do that. Also, small, seemingly innocuous updates, they all must be signed and validated as well. Small devices not in the boot path that have firmware, keyboard firmware and other things like that. A lot of times it's not properly signed and not secure, etc., and no one checks it. They just slam it in there. Well, gee, those can attack systems after the fact. They don't necessarily run in the boot path, but later on in the system, they can do really bad things. So make sure that every piece of firmware gets updated and secured properly. Now, here's an important one to me. Data must be protected as well, not just code that gets executed, but the data that's used. Code and data must be from a confirmed valid source, protected in transit, signed or encrypted or both. Should be signed when it's at rest. For example, in the UEFI disk partition. Avoid time of check versus time of use errors. Again, the idea, check it and then make sure that you use it immediately, or you copy it into an inaccessible buffer or whatever, so that people don't change it out from underneath you. And the example of the data vulnerability here are the three CVEs here. They're really the same flaw. An unsigned image file from the UEFI partition triggered a flaw in open source image processing software that displays a splash screen. And I'm sure the folks on this call, this webinar, are probably familiar with as logo fail, and resulted in potential of denial of service and or privileged access to things that they shouldn't have. All of these vulnerabilities were, quote, fixed by fixing the bug in the open source image processing software that caused the problem to go away. My concern, and this is a personal concern of mine, and I want to say that not necessarily everyone agrees with me, but I believe that it is incorrect that the data, in this particular case, an image file that was loaded into the UEFI partition, was not tested and signed, and that when it was read into memory and handed to the open source image processing software, that it should have been checked, the signature of it should have been checked to make sure that it had not been altered. I believe that in this particular case, that we should not allow unsigned data from a disk drive that no matter who knows how it got there or where it came from. Just because we fixed this particular bug in the image processing software doesn't necessarily mean that there aren't a bunch more vulnerabilities in image processing software or other software that uses data that gets loaded out of the UEFI partition. So I believe that we should be only loading signed data. Again, personal opinion. So more specifically here, in the firmware space, drivers that rely on UEFI variables must have defaults that, in case the variable is not present or has been corrupted, verify the variable values are in range before you use them. Make sure they make sense. Have a default working code path if a variable is deleted, missing, or has been corrupted or changed inappropriately. For management mode stuff, SMM and Trust Zone, they have access to private data areas, may contain security secrets and sensitive data. Traditional antivirus software can't see them and can't deal with them. They must do input validation and buffer handling appropriately. And any management mode interfaces not needed at OS runtime should be disabled. Exit boot services should be disabling any SMM stuff that's not needed. So we're nearing the end here. The call to action: talk to your senior corporate management and make sure you have leadership support for a Secure by Design program. If they've never heard of it, then they need to be educated. You'll see in the references at the end the pointer to the document that describes Secure by Design program by the U.S. government. But there are plenty of things out there that you can find to educate folks and explain to them the importance of this stuff. Implement it. Don't just talk about it. Don't just read the document and say, yeah, that sounds good. And yeah, we'll work on that as we get a chance. Make sure you have a program to implement it appropriately. And one of the things to do that is that upward management slide that I did, where you need to talk to your boss to have him talk to his boss or her boss or whatever, and make sure that all the way up the chain of command to your CEO needs to understand about this. And then understand what zero trust really means in your environment. What can you do to make sure that you have an appropriate level of trust where it makes sense, that it's explicit, that you understand how trust is managed, where your roots of trust are, who owns those roots of trust, and that you can follow and get appropriate attestations that the system you're talking to, the service you're talking to, or is contacting you is what they say they are, and that you can trust them to do the right thing in your environment. So make it part of your everyday system design. So, time for questions.
We'll begin the opportunity for any viewers to ask questions at this time.
And while we're asking questions, I'll put up my references that I mentioned before. This URL is a pointer to the U.S. government document published by CISA, the NSA, FBI, etc. And I drew a bunch of the material in this webinar from that. Also, there's an excellent book on trust in computer systems and the cloud. It does talk a lot about networking, but it's an excellent book on trust and what that really means. I recommend it. These will be in the slide deck that eventually gets posted in the next few days up to the UEFI site.
It looks like we don't have any questions today. I'd like to thank you all for coming to today's UEFI Forum webinar presentation. Thank you again for joining, and like Dick said, we will upload these slides to the UEFI Forum website following this broadcast. Thank you all.